We have Joe Weichelman here, representing himself, Felipe Nunez, Joseph Stegman, Justin Nichols, Georgie Sherbatchik, Marie Ryu, and Aaron League. And they're going to talk to us about luminescent solar concentrators and the harvest of solar energy. Take it away, Joe.
All right, thank you so much, Dr. Hein. My name is Joe Weichelman, and today I have Felipe Nunez and Justin Nichols here helping me present today. And we'll be talking to you about solar luminescent concentrators and how we can use these to harvest solar energy in a clean way. Let's see. There we go. So in this presentation, we're going to talk about what luminescent solar concentrators are and how they work. We're also going to look a little bit into the luminescent species, which we'll get into more in the future. We'll talk about what we accomplished this year, and we'll also go into the plans that we have for the upcoming years. So an introduction to luminescent solar concentrator. I'll refer to those as LSCs to abbreviate that because it gets a little hard on the tongue after a while. But what you see in this image over on the right here is an example of one of our luminescent solar concentrators. So this microscope objective right here is focusing a laser beam onto the surface of this luminescent solar concentrator. And as the light is passing through, it's being absorbed by dye present inside of this plastic, and that dye is then re-emitting. And what happens is all the light that is or not all the light, but a good portion of the light that's re-emitted can then be concentrated around the edges. And that's why the edges of this plastic are glowing. And that's the end goal for this, is to have a piece of plastic, essentially a window that allows most light to pass through, but some of that light is absorbed and propagated towards the edges and concentrated, where it can then be turned into electricity by photovoltaic cells. Now, these can be made in a lot of different geometries, and what we're going to be looking at mostly is a sheet. So like I was referring to before, a tinted window is essentially what we're trying to create. The reason that this plastic here is pink is because we're using a rhodamine B dye, which emits along a kind of red-pink spectrum. But that's the introduction. Now we're going to go into more about how they do this. So I'd like to draw your attention to the upper figure right here. Basically, you have light incident upon a transparent medium. And as light travels through this transparent medium, it has a chance of interacting with a luminescent species. And what this species will do is it will absorb that light energy. It'll enter a brief excited state, and then it will collapse and release that energy in the form of a photon. And that photon, that beam of light, can be emitted at almost any angle. And if that angle is just shallow enough, we can reach something called total internal reflection. Now, this is a function of the index of refraction of a material. So if I now draw your attention to the lower diagram, we have two materials here. We have air and we have water. So water has a higher index of refraction than air does. And the result of this, you can see here, there's a beam of light that passes out of the water into the air, and it gets bent. Now, the greater the difference in the index of refraction, the greater that beam will be bent. And at some point, we reach what's called the critical angle. And past that critical angle, we have total internal reflection, which is what I was referring to before. So if those luminescent species within the plastic emit past this critical angle, all the light that is emitted at that angle will then be propagated and bounce back and forth. So we'll look at a animation of this process in the next slide. The luminescent species that we can use are dyes. As I previously mentioned, we have rhodamine B as one of our kind of placeholding dyes. And then what's really exciting is we have quantum dots, and we'll talk a little bit more about that in a future slide. And the end goal would then be the electric yield. So after the light has been concentrated at the edge of the plastic, at this upper figure, again, you can see there's a solar cell along the edge, which can then turn the concentrated light into electricity. So here is an animation. So this is the plastic, and these dots are the luminescent species. So what happens is a photon is incident upon this plastic. And as you can see, it bends as it enters. That is an example of the index of refraction changing. It is incident upon one of these particles, and it's glowing to show you that it's now entered an excited state. And after a brief amount of time, it can re-emit that light. And that light, if it's at the proper angle, can then be bounced back and forth using total internal reflection. Now, one of the issues that we can have is that if we're using a dye or a quantum dot, some sort of luminescent species that can absorb and emit the same wavelengths of light, then the emitted light from that first particle can be reabsorbed by another particle, and it has a chance of escaping again should the light be emitted at something above the critical angle, something that won't allow it to have total internal reflection. So this is something that is really important, and we're going to go ahead and talk about that in the next slide. This is where the quantum dots become important. So the luminescent species, as I mentioned before, we have rhodamin B and PMI. Those are some dyes that we've worked in the past. But the problem with them is that they're not tunable. We can't really change a lot of their properties along the emission and their absorption. This is where quantum dots really sell their case, because quantum dots are completely customizable. We can have different types of quantum dots made of different materials that have different ranges that they work in. And they also emit and absorb along different wavelengths. So this allows us to separate the emission and the absorption in such a way that light passing through can be absorbed. It can then be re-emitted at a different wavelength that can't then be reabsorbed by other quantum dots. There are a few challenges working with these. They don't like oxygen, and we have to work with these guys in a completely nitrogen atmosphere in order to preserve them during any sort of synthesis or immersion into the plastic matrix. And that's posed a very difficult thing to do. So now I'm going to invite Felipe Nunez to talk to you a little bit about some of the stuff we've accomplished in regards to the plastic and its mold.
All right. So what we have accomplished so far, we made a new design for the plastic mold. So the main goal for the new design was to be airtight. We also were looking for durability and a way to reuse the seal. However, the new design was not that successful as we thought. And we got a gas permeability problem, so it wasn't airtight as we thought. And also we got a thermodynamics problem, because if you check the picture of the new mold here, we have a lot of material here, the frame, the aluminum frame. So we have more surface area, and the heat when comes in, the MMA evaporates easier and quicker.
All right, thank you, Felipe. This is going back to the luminescent species and the quantum dots. We have a closely related project that has been working on quantum dot synthesis and design. They presented earlier today. This is kind of a little synopsis, a little summary of what was accomplished, because it's still very, very important to what we're doing. This is an example of absorption and an emission spectra of one of the quantum dot samples that we made in-house. And this is wavelength along the x-axis and intensity along the y-axis. This red line you see here is the absorption, so it's what the quantum dots can absorb, and this blue line here is the emission of the quantum dots. And as you can see, they don't quite line up, and that inability for them to line up is a Stokes shift. So we can change how much they move relative to each other based off their size. And a lot of the developments that have been made in this area are that we've been able to actually measure the emission, which is very difficult to do. Our quantum dots emit in the infrared spectrum, which means their beam is not visible to the naked eye. So it's very difficult to take a measurement of, but we were able to accomplish that. And we have a lot more insight through the synthesis and the measurements that we've been taking for how to create good quantum dot populations. And we now are able to get a pretty good idea for how to get the perfect quantum dot for a luminescent concentrator. This is kind of the pinnacle of this last year of work. We actually were able to successfully integrate live quantum dots into a piece of MMA plastic. And this is a photo of it right now. It doesn't look super impressive. It's not the window that we were showing you earlier, but this is kind of a milestone for us because we were able to get quantum dots out of their toluene environment without damaging them. And we were able to transfer them to a piece of, to a plastic, and we were able to get that plastic to polymerize without damaging the quantum dots. And all this was done in a nitrogen atmosphere, and it was rather challenging, but we learned a lot in the process. We don't have a great emission reading, but the procedure is the important part. Now that we know how to do this, we can, we only have upwards to go, right? We can just improve on the procedure and try to create a better concentrator. This is also exciting because it opens the door for measuring the quantum yield or the electrical yield. So we can now create actual LSCs and try to measure how much electricity they can produce as a function of how much light is passing through them. And we actually have developed a device to help us do this. So I'm going to invite Justin Nichols to talk to you a little bit about this development.
So we were able to design and 3D print this solar capture device. It'd essentially be the window frame for the plastic. And you can see there, you got a little slat. I'm going to show on the computer. This slat would be just the spot where we'd be able to insert it. And we've got the photovoltaic cells on these blue slats wired in series so we can get a voltage reading from them. It was our second design. This one's a little bigger than the first one. It was actually a little too big because it'll be after we cut and polish and get the edges fine down. It ends up being too small. The one we used last year, we weren't able to use because of COVID, of course. And it was really small because it was too small for our samples. So we weren't really, we knew we needed to go up a size, but we kind of needed to find a Goldilocks in between the big and small 3D prints. So.
All right, thank you, Justin. I also want to add that this is essentially the window frame for the piece of plastic. You can think about the plastic lying in here and this acting as a frame holding the window. So as light passes through, the light's propagated to the edges and collected by the photovoltaic cells. So this is an exciting development for us. This is some other work that we've done that we're going to continue working on. So the nitrogen casting in the glove box, the small scale prototype that we made, we were able to do in the fume hood under flow, nitrogen flow. But for full casting, we're probably going to have to use an actual nitrogen atmosphere in this glove box. And that includes the quantum dot isolation and the quantum dot immersion. A lot of that probably will have to happen in here. So we've done some work on how the procedure will look to accomplish this. And now that we have a successful immersion, this will be a lot easier to attain. Now I'm going to talk about our plans for the future. So the things that we're looking for in the next, in the upcoming years are going to be quality control with the plastics. So that's going to depend largely on the mold that we make and trying to find something that doesn't have negative thermodynamic effects and something that's able to be airtight and hold the plastic in. This is a really important part of the process to keep the oxygen out and keep the plastics clear and nice. We have to work more on the refining the procedure for integrating the quantum dots into plastic, because even though we've done it once, That doesn't mean that we can do it routinely, and it doesn't mean we can do it well every time. So we have to work and refine the procedure and get it tailored to meet our needs. We also need to measure the LSC absorption. So now that we're able to make luminescent concentrators, we would like to be able to actually measure how much of the quantum dots are still absorbing and still emitting. And in the end, that's just going to lead to measuring the electric yield. So the exciting culmination of everything, actually getting some power out of a tinted window. That's going to be a major milestone that we're looking at in the near future. So I'd like to give credit to the following. And I would also like to, at this time, open the floor to any discussions or questions that people have in mind. Thank you.
First, I think, it's a shame that we can't be in the same room. I think anybody who wants to unmute their mic and give a little bit of gentle applause might be appreciated. So it was a good talk. I have a question. Can I ask this? It's probably a really bad question.
Go ahead.
It's probably really bad, so I drew a diagram so that it at least makes sense. So do you have control over where the dots are? Like if you were to arrange them close to the boundary, tightly packed, if you could do that, I mean, would this encourage more interaction when they have a bad angle and less interaction when they have a good angles to kind of increase your chances of collecting light? So it's kind of two questions. Can you choose how to place them? And is there some favorable way? Or like this was a bad idea. I drew also like trying to match the angle of bouncing with the placement of dots. Probably okay. So probably two dumb questions.
No, those are valid questions. Controlling the geometric placement of the quantum dots is something that we have not really considered too much, mostly because it's going to be something very difficult to control. Trying to immerse these particles into a plastic, what we can control is the density. So we can control how much of this luminescent species we immerse into a certain volume of plastic, but trying to position them would be extremely difficult. I'm not entirely sure how we would manage that. It's possible that we could increase the concentrations towards the edges by maybe pre-polymerizing a piece of plastic in the middle. However, the geometry or the placement of these quantum dots shouldn't matter as much if the absorption and the emission spectra are separate. So there's definitely some possibility and something to look into there, but right now we haven't really gone over that option. Thank you, though.
Yeah, thanks.
I have a question in the room.
So can you tell me more about the quantum dots and are they bound to some metal or things involved in quantum dots? Can you tell me more about those?
Yeah, absolutely. So the question was more information about quantum dots, basically, what they're bound to, and a little bit about the ligands. So quantum dots, the ones we're working with are lead sulfide. So they're a kind of crystalline structure of lead sulfide molecules. And they basically can crystallize into different sizes, and that's dependent on how they're synthesized. And the size that they're at is what largely controls their emission and their absorption. So it controls the band gap from the valence of the conduction. And they do have, they can have ligands. So in our synthesis, we use oleic acid, and that has the potential to act as a ligand that bonds around the quantum dot and it basically like acts as a safety envelope. It protects it. But there's also things you can do to swap the ligands out should we decide to have different amounts of casing, or if we want to put it somewhere where it needs to be more stable. So yeah, they can have ligands bonded to them to help protect them. And we have oleic acid that's functioning for that currently. Does that answer the information? Thank you. Any further questions?
I have a couple of questions.
Go ahead.
So my first question is, so you mentioned how you need to keep the quantum dots away from oxygen. How do you do that when they're just like sitting on a shelf? Do you have them in a nitrogen filled vial or something like that?
Yeah, so the storage is not as much of an issue. When we store them in little vials. There's not a whole lot of volume of air present in the vials. And I'm sure there is some damage that occurs to the quantum dots with the oxygen that is in the vials. However, we have measured long-term emission or long-term absorptions of the quantum dots, long-term meaning over the span of a year or 2 years. And there was next to no decline due to any oxidation. So I don't think that the actual storage is an issue. The synthesis is an issue, however, because when you have these quantum dots moving around or the fluids being exposed to moving convections in the air, that's when you can get a large exchange of oxygen to the lead sulfide, and significant damage can occur there if it's not if it happens for too long. So what we do is we have them in rather closed vials. We have a 3-necked flask. We stop one of the necks, and then the other one of the necks has nitrogen flowing through it and out the other. So as we're heating the quantum dots, or as we're isolating them, they're under nitrogen flow. And as previously said, we're probably going to have to do this in a completely enclosed environment in the future.
Okay. And then my second question was just about encasing them in the plastic. What kind of plastic do you use for that?
So that's a great question. Thank you. I meant to bring this up earlier in the presentation. We're using polymethyl methacrylate plastic as our medium. These can be done in glass, but it's very, very, very difficult to work with. And there's a very high potential of damaging the quantum dots in doing so. So as kind of like a prototype, we're using plastic to be able to house the quantum dots. And the plastic that we're using is relatively easy to work with. It's fairly cheap, and it also has a very similar index of refraction to glass. It's about 1.5. So it's just kind of an ideal candidate for its transparency and its ease of use.
Okay, so would it be that the heating the glass, you would have to heat up the glass in order to encase the quantum dots, and that would potentially damage them?
Yes, we also don't currently have any the equipment necessary to be able to form glass around quantum dots.
Mm-hmm. Okay, thank you.
No, thank you.
All right, well, let's thank Joe and his group again